Hey guys, so this is something new that we haven't discovered or talked about, I should say, before, and these are just called heating curves. Okay, it's the way that I guess molecules react going from their solid states to their gas states. So let's say that here that we are talking about water. Okay, we see this heating curve and we think, okay, what in the heck is going on? Well, this is just the temperature, like observing the temperature of ice as it goes from a solid to a gas. So we have temperature on the left side and we have time on the bottom. And what we're doing here is that we got ice as a solid block down here and we're heating it up and we're seeing what happens. So we have ice and we're heating it up, we're heating it up, we're heating it up, and then it gets to that 0 degrees Celsius, right? That's where it's starting to make its transition from a solid to a liquid. And then all of a sudden, even though we're adding more heat, the time is staying flat, or the temperature is staying flat. So we're adding more heat, but for some reason, it's not heating up that ice anymore. So what is happening? Well, energy is going into trying to weaken those intermolecular bonds, okay? Not break them, but weaken them. So what's happening here is we heat it up, it gets to that point where it's ready to turn to a liquid, and it flattens, okay? So you have a nice little transition period of ice and a liquid here, where we haven't got it completely to liquid yet, but we're heating it up a bunch, and we're trying to break those intermolecular forces and get those water molecules spread out a whole bunch. And this is called the heat of fusion. This little plateau is the heat of fusion. And then after a while, we put enough heat in there that all of a sudden the temperature of the water starts to increase again. Okay? It's increasing, it's increasing, it's increasing. We're adding more heat over time, and it gets to 100 degrees Celsius. Now we flatten out again because now we are putting energy into completely breaking those intermolecular forces. So this plateau, it didn't take that long to change it from completely to ice to liquid, but here we might see something where it takes a lot longer because we are now breaking those intermolecular forces. So we'll add a bunch of heat into that liquid. We are trying to break away those H2 molecules so they become individual H2O molecules bouncing around, so it takes a long time. And then after that last intermolecular force is broken, we can start heating up again and raising the temperature and making those water molecules go a lot faster. And this little plateau is called the heat of vaporization. Okay? Makes sense, right? We're vaporizing it. So heat of vaporization, down here, heat of fusion. What they love to do is give you different steepness of these heat curves and ask you questions about them. So they might say something like, this from, let's say this is negative, 50 degrees Celsius. From negative 50 degrees Celsius to 0 degrees Celsius, the curve was shallow. But from 0 degrees Celsius to 100 degrees Celsius, the curve was steep. Why? What inference can you make about ice's specific heat compared to water's specific heat? So they'll ask you things like that, okay? So they'll ask, what is the comparison between ice's specific heat and water's specific heat? Well, this guy was really shallow, right? So that means it took a long time in order to get it to ice, right? It took this much amount of time. But if you look at water's curve, it's a nice steep curve. So it only took this much time to heat it 100 degrees Celsius. Okay, so you could say that, oh, the specific heat of ice is actually lower than the specific heat of, the specific heat of water is lower than the specific heat of ice, right? This took a long time to heat up. That means it's got a high specific heat. This one took a very short time to heat up. It's got a small specific heat. It'll ask you things about these flat curves. They'll say, why is this flat curve longer than this plateau? Why is the heat of vaporization why did it take so much time to vaporize it compared to heat of fusion? And that's when you'd say something like, we're actually breaking the intermolecular forces here. We're separating those H2O molecules completely so they're not attracted to each other whatsoever, whereas right here, we're just weakening them. We're weakening those intermolecular forces so that they separate a little bit and go from that solid state to that liquid state. So this is just an intro to this. I just want to show this. They'll ask you a bunch of conceptual problems about it. There are some calculations you can do with it, but we're not doing that. Okay, so no worries. Just be ready for some conceptual questions on stuff like that. Have a great day.